Can we have examples of instances where there are forces acting but objects do not move? Of course. If you look at this corner there, are there forces acting? Oh, so many forces. It's pushing back, towards the sides, weight acting down. But when the engineer built it, didn't he have to take care to see that the forces are balanced in all directions? Along the x, y, and the z. The net force must be 0, right? There are two conditions for static equilibrium. That's the first condition. The net force along any direction must be 0. Now, I'm just trying to show this by an example. If you have something like a meter stick suspended, as you can see, a meter stick suspended there, not exactly at the 50 centimeter mark, it's probably closer to the 30 centimeter, right? 30 or 40. And you have two masses hanging down at the ends. What can you say about the total forces acting down and the tension in the string if this thing is not moving? What can you say about the total downward force and the tension in the string? They should be equal. And in opposite directions. Exactly. That's what you mean by, well, in this case, you're only looking at the y-axis. So the net force along the y-axis in this case is 0. Right? So that some of the forces in the downward should always be equal to some of the forces in the upward. In this case, there's only one string. But what if there were two strings attached? Then you would have two tensions. Not necessarily equal, but definitely the sum of the two tensions upwards must be equal to the sum of the forces downwards. So that's the first condition for equilibrium. Okay. I've labeled the forces F1 and F2. The tension is Ft or F3 in this case. Therefore, according to the second condition, the first condition, second, net force is equal to 0, which means F1 plus F2 is equal to F3. Looks like a very simple relation, which it is, but very crucial, very useful. Now, to get to the second condition, remember that forces are also capable of rotating something. We just finished that chapter, right? So forces are capable of moving something forward or rotating it. When you talk of stable or stability, you do not want it to rotate. You do not want it to move. You do not want it to rotate either. Now, if you do not want it to rotate, then definitely the net torque must be 0. The net torque must be 0. Maybe now you're saying, what is torque? What is torque? How do you calculate torque? The symbol is tau. Gone. The spring break, everything washed out. Okay. What? It's actually RF sine theta, R cross F. Or in the most simple case, it's the product of the distance and the force. Distance and the force. For example, if you have something that can rotate about this axis, that's the axis of rotation, let's say A, and you apply a force perpendicular to whatever that is, let's say it's a door, and these are the hinges. Isn't that the axis of rotation? So if you apply a force F here, and the distance between the line of action of the force and the axis is R, then the torque is the product of the two. So if you look at this diagram, you see there are two torques acting. One is trying to rotate it in the clockwise, the other is trying to rotate it in the counterclockwise. Can you name them for me? Which one is trying to rotate it in the clockwise direction? Which are the forces? F2. F2 is trying to rotate it in the clockwise direction because that's what you mean by clockwise, see? You always have to have the axis in perspective. Isn't that the axis of rotation? Okay, so that's trying to rotate it clockwise, while F1 is trying to rotate it counterclockwise. Therefore, if the net torque must be 0, then F2 times this distance, which I did not, let me call this C, okay? If this point is C, then F2 times BC should be equal to, can you complete it? F1 times AC. 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 F1 times AC, because you always take the distance from the axis of rotation. Now, we could have done this in another way. I'm not trying to make it complicated, but I want you to understand this. We could have calculated the torques about the point A, which means you just consider that that is the axis. It's still going to work out correctly, but there is a problem. With this point in perspective, F2 is still going to be clockwise, but it's going to be F2 times, help me out, AB. And what's the counterclockwise? F3. You see, F3 is the one that's trying to rotate it counterclockwise, and that would be F3 times AC. What about F1? It does not have any torque at A. Reason? The distance is 0. Now, if this part of the chapter is clear, that's the end of the first part of this chapter. Two conditions. Number one, the net force is 0. Number two, the net torque is 0. And I just defined what that means. You can take the axis of rotation at any point, or you can calculate the torques about any point. It'll still work out correct. There's a meter stick like this. It has a center of mass, isn't it? How could you find its center of mass? Oh, by simply balancing it. Have a string and balance it. Whatever point it balances at exactly will be its center of mass. That's easy to say, but not that easy to do. That's what you're going to do in the lab first. You'll be given a meter stick, you have to balance it on a knife edge. So that's going to be really, you have to do this lab exactly, and your grade depends on how close your numbers are in this one particularly. So you first find the center of mass. Let's assume that the center of mass is at 50. It'll be close to 50. Not necessarily 50, right? But let's say it's 50 centimeters. Are you with me? Okay, so you have the situation. The center of mass is at 50. That means the mass of this meter stick is acting through 50 centimeters. And I think I assume this mass is 100 grams. Just assume. So the mass of the meter stick, which is 100 grams, is acting straight down through 50 centimeters. Right? I'm trying to break it down into small parts. Now, second thing, if I have a string exactly at 50 and suspend it, like you see in the diagram, will that be in equilibrium? Yes. It'll be, right? Okay, what will be the tension in the string? The weight, which you could write as 100-gram weight. So in this case, you need not change it into kilograms and multiply it with G and make it in newtons. No, just put it as gram weight. That's a unit of force, which is accepted in this case. Okay, so that makes it easier. So the tension in the string is 100-gram weight, correct? Okay. Now what I'm going to do is, I'm going to suspend it not from 50. I want to suspend it from 20 or 30. The major mistake that students make is this. Where is the center of mass of this meter stick? 50. Okay. It's still at 50. No matter where you suspend it from, its center of mass is fixed. The center of mass of any object is a fixed point. Does not depend on where you're trying to balance it. You try to balance it here, it's not going to balance. It's not going to balance because its mass is trying to rotate it from here. See, the center of mass is fixed. But the axis of rotation changes. In the first case, the axis of rotation was here, but now the axis of rotation is here, isn't it? Now, can you balance this by using another mass that I give to you? Which side would you have to put it on? These are just silly, simple questions. Where would you have to put that mass on? You would look like a big fool if you put that mass here. Because there's already the mass of the meter stick acting down to this point, so you'll have to put it on the other side, right? Okay, so if I tell you, that's the second part of the lab that you're doing today. So if I tell you that you have to put it at 10 centimeter, okay? And you have to find the mass, go ahead and find that mass for me. Go ahead. Find that mass. The clockwise is 100 times 30. See, it doesn't matter whether it's in centimeters as long as it's the same unit on both sides. It'll cancel out. 100 times 30 is equal to m times 10. The mass here is 300 grams. Only then can you get it to balance. All right. You have to calculate the forces, Fa and Fb, at the supports. That's the person. The weight of the person acts vertically down. It's 58 kilograms times 9.8. In this case, you need to have it in newtons. 568.4 newtons. Okay. The force at B is upwards, like I told you. But remember, the force at A is down. You see, that's what I was trying to explain. And what is the first condition? For equilibrium, the forces in one direction should be equal to the forces in the opposite, right? So your condition would be Fa plus 568.4 is equal to Fb. All right. So first condition. Yeah, those are the distances. Fb is Fa plus 568.4. Now let's try to apply the second condition. And you can see that I'm trying to calculate the torques about this point. Okay? So I want you to get this. What is the torque due to Fa at that point? What is the torque due to Fa? Nothing, right? Zero. What about that due to Fb? Is it clockwise or counterclockwise? You have to keep this in perspective and say, all right, this is trying to twist it that way, isn't it? It's counterclockwise with this point in your perspective. Come on. What about this force? Isn't it trying to turn it clockwise? Okay. Therefore, we're going to say 568.4, be with me, 568.4 times, help me out, 4 meters should be equal to Fb times 1 meter. Problem done. Remember that in the first part, we're not considering the weight of the board. Do you see that? We're not considering the weight of the board. So, Fb times 1 is 568.4 times 4. From there, you get Fb. Once you get that, substitute it back into the first condition and get Fa. It's going to be this take away 568.4. So that is 1705.2. Now in the B part, you have to consider the mass of the board, which is 35 kilograms. And because, see, it says assume the board's center of gravity is at its center. See, right? That means the center of gravity is exactly at the center here, which is 2 meters away from end A. Right? So the additional force is 35 times 9.8. And you apply the same conditions. Same conditions again. But this time you're going to say Fb is equal to the sum of the 3 forces acting down, isn't it? There are 3 now acting down. So Fa plus, well, the 911 is obviously the sum of these 2. And then again calculate the torque about A, and you get Fb times 1 is 343 times 2. Let me stop it right there. Look, 343. Isn't this distance 2? Isn't this distance 2? Come on. That's why it's 343 times 2 plus 568.4 times what? 4. Okay, calculate that. You get Fb. Once you get Fb, substitute it back and you get Fa.
You know it's 2 because the mass is in the center, right?
Which one? Yeah, because the center of gravity is exactly at 2.
Okay.
So you get Fas 2048.2. It's a long board, and two people, 75 kilograms at one end, 25 at the other end, and you got to find out where you have to have the pivot, isn't it? Obviously, it has to be closer to the heavier person. That's just common sense, right? So I'm considering that distance to be x, in which case this will be 9 minus x, because the total length is 9 meters. Now, if you take that pivot as the axis, then there are two torques. This is clockwise, and this is going to be counterclockwise. Clockwise is going to be 75 times 9 minus x, and counterclockwise is 25 times x. Now the little math that you have to do is to find x. From that, you get 735 is 100x, and x is 7.35 meter from where the child is seated. In the B part, if you have to consider the mass of the board, which is 15 kilogram, and it says the board is uniform. Do you see that? If it is uniform, then surely its mass is acting right down through its center. So now, it's going to be 15 times 4.5 minus x. Where did I get that 4.5 from? Because it's right at the center. It's 4.5. So 4.5, because I took this as x, and this is 4.5. Right? Okay, 4.5 minus x plus 25 times x should be equal to 75 times 9 minus x. So you solve that. Again, you find x. That's a little algebra there. And you get 85x is equal to 667.5, and x is 7.85 meter, which means this time you have to push it further towards the pivot, which should make sense, isn't it? Let's take a look at this distance that I took. Is it 4.5 minus x? This is x. Where am I calculating the torques? This point, isn't it? So this distance is x, this is 4.5, so this should have been x minus 4.5, isn't it? I just noticed that. Oh, goodness. All right, in this question, the meter stick, mass 180 grams, it's uniform, so its mass is acting straight through the center, and you have the two strings at 0 and 90, so 180 grams right down through the center. Condition 1, total upward force is equal to total downward. Ft1 plus Ft2 is 180. And I'm calculating the torques about 0. Therefore, 180 creates a clockwise moment, and that is 180 times 50 is equal to Ft2 times 90. And what do you get for Ft2? Hopefully this time I got it right. Is it 100? Hey, okay. Put it back into that, you get Ft1 is 80 gram weight. The mass of the sheet is 0.60 kilograms, and it's right at the center. How do you know it's at the center again? Because the angles are equal, isn't it? Both the angles are 3.5 degrees. Once again, remember, this is a highly exaggerated diagram, and you're supposed to find the tension. Tell me this. What can you say about the tensions on both sides? Same. All right. Therefore, if I take this tension as Ft, okay, that angle is 3.5 degrees. And the other side is going to be Ft, and resolve this force into two components. Well, that is the weight, which is 0.6 times 9.8, 5.88 newtons. Now resolve the force, the tension, into the two components. And I'm going to get this vertical component as 2Ft sine theta. Why? Okay, because when you resolve this, this is going to be ft cos theta. Surely this angle is 3.5. You see that? So this is ft cos 3.5. This is also ft cos 3.5, isn't it? So they cancel out. Equal and opposite, they cancel out, but their vertical components add up because each one contributes ft sine theta, and there are two. Therefore, the total vertical component is 2ft sine theta, which should be equal to, come on now, 5.88, problem done. 2ft sine theta should be equal to 5.88. Isn't that the condition? One of the conditions? That the total forces in the up should be equal to the total forces in the down. And since you have the angle, all you got to do is calculate ft from that. Do you think ft is going to be small? 48.16 newtons. That's because the angle is small, because it was stretched initially, you see? So that's why. So the person wants to push a lamp across the floor. The mass of the lamp is given. The coefficient of friction is given there. You have to find the maximum height x above the floor at which the person can push the lamp so that it slides rather than tips. So two cases. That's the diagram coming up. And I give you the diameter as 24 centimeter. Okay, I'm going to calculate the torque about this point. That's what it shows, right? About that point. Okay. mg and the normal reaction, but you know the normal reaction is mg, and therefore you can calculate friction. In this case, because it should just slide, the applied force must be equal and opposite to friction. So the applied force Fp is equal to friction, which is mu Fn, which is mu mg. And then, when you apply the force here, you see that this force creates a clockwise torque, right, about this point, while Fn creates a counterclockwise. You see that? According to the diagram that I've drawn. Fn creates a counterclockwise. Okay. So Fn times 0.12 should be equal to Fp times x. Speed that up. So x is Fn times 0.12 by Fp. Fn is mu mg, so you substitute all that, the m's cancel out, the g is gone, and it's just 0.12 by mu, which is 0.60 meter. So the maximum you can do in this case is apply the force 60 centimeters above, 0.60 meters. If you go anywhere higher than that, it's not going to slide, but it's going to tip over. Well, in this question, a 75 kilogram adult sits at one end of a 9-meter long board. This is where he's seated. And a child, 25 kilograms, sits at the other end. The question is, where should the pivot be placed so that the board is balanced? And in the first case, you ignore the board's mass. So in the first case, you do not have this 15 kilogram. Okay, so in the first case, you do not have this. And let's take this distance as x. And therefore, this must be 9 minus x, because the total length is 9 meters. And calculating the torque about this point, you see that this is going to create a clockwise torque, while this is going to create a counterclockwise. And this is 75 times 9 minus x. That should be equal to 25, which is 25 here, times x. So that's why we have, hold on. All right, that's why we have 675 minus 75x is equal to 25. Take this to the other side, becomes 75 plus 25, which is 100x, from which you get x is 6.75 meter. In part B, now you have to consider the mass of the board, and because it's a uniform board, its weight or its mass certainly acts through its center, because that's where the center of mass is. So the 15 kilogram acts right through 4.5 meters. And now when you look at it, look at the situation, since the pivot is here, you see that now there are two counterclockwise torques. One is by the 15 kilograms, the other is by the 25. And there's only one clockwise. Okay, therefore 15 multiplied by this distance, and this distance is x minus 4.5, right? Because the total distance is x, and this is 4.5, therefore the remaining distance must be x minus 4.5. So 15 times x minus 4.5 plus 25 times x should be equal to 75 times 9 minus x. And when you do the math, you get x is equal to 6.46 meter. You got to distribute carefully. There's a negative here, and you collect the x terms on one side and the number on the other side and divide, you get 6.46. In this question, three children are trying to balance on a seesaw, which consists of a fulcrum rock acting as the pivot, and it's a very light board, 3.6 meters long. Two playmates are already on either end. The boy has a mass 50 kilogram and the girl a mass of 35. Where should another girl C be seated whose mass is 25 to balance the seesaw? Okay, so that's the seesaw, that's the rock acting as the fulcrum. One child is here, the other is at the other end. The length is given as 3.6 meters. So A has a mass 50 kilogram, B has a mass 35 kilograms, and let's assume that the third person is seated at a distance of x meters from the rock, the pivot, and she has a mass 25 kilogram. So the diagram should now make sense, and if it does, then calculating the torque about this point, you see that there are two clockwise and one counterclockwise. 35 and 25 create the clockwise, while 50 creates the counterclockwise. And so, 35 times, let me write that, taking moments about the fulcrum. So, you're calculating the torque about the fulcrum. 35 times this distance, which is 1.8, plus 25 times x should be equal to 50 times 1.8. And when you calculate it, you get 1.08 meter. So that's the distance from the fulcrum at which the third girl C should be seated. Alright, number 7, you have a 140 kilogram horizontal beam supported at each end. So it's supported at each end, and a 320 kilogram piano rests a quarter of the way from one end. So I've divided this into 4 parts, 1, 2, 3, and 4. So the piano is here, 1/4 away from one end, from this end. And you got to find the vertical force on each of the 2 supports. You've got to find the force on this and this support. And remember that the mass of the beam itself, which is 140 kilograms, is acting right through its center. So that is 140 kilograms. And the piano is here, so which has 320. So 2 forces down and 2 forces up. So that's 140 kilograms. So changing it in newtons. And the forces at the supports are F1 and F2 upwards. This is 3136 Newton. Now condition number 1, the sum of the forces F1 plus F2 is equal to the sum of the forces down, which gives 4508. And then you calculate the torque about, you can calculate it about any point, but I'm taking it about A. And when you take a careful look about A, you have 1, 2 trying to turn it in the clockwise direction, but you have F2 trying to turn it in the counterclockwise. Therefore, 3136 times this distance, which is 1/4, plus 1372 times 1/2 should be equal to F2 times 1. Now I've considered that the total length of this beam is 1. So when you calculate, you get F2 is 1470, and take it back into the first equation and you get F1. This question, the Leaning Tower of Pisa is 55 meter tall, about 7 meter in diameter. Top is 4.5 meter off the center. Is the tower in stable equilibrium? If so, how much further can it lean before it becomes unstable? Now, to see whether it's in stable equilibrium, what you've got to do is draw a vertical line from its center of gravity or center of mass. If that vertical line falls within the base, inside the base, then it is stable. But if that vertical line drawn from the center of mass falls outside the base, it's unstable. So let's complete the diagram now. You take that off, and okay, this angle is so small. Let me get the whole thing. Okay, there. Now remember that you have 2 triangles here, both right angle triangles, 1 and 2. And actually you need not take tan theta here, and even if you do, it's okay, because theta is small. When theta is small, tan theta is exactly the same as sine theta. So what I've written actually is sine theta, but which could also be written as tan theta, because angle small, sine theta will exactly have the same value as tan theta. But you did not even do all that. You can even do it like, these are 2 similar triangles, correct? So if you take the ratio of the corresponding sides, they must be equal. In the first one, the smaller one, I'm going to take x divided by 27.5. It's a half of 55. Should be equal to 4.5, because that's how much it can go, divided by 55. See, because it says the top is already 4.5 meter off the center. See, that's what this shows. Remember, I've drawn this line from the top. So that line, you see this line is 4.5 meters off the center. So that's 4.5 divided by what? 55. Should be equal to x divided by 27.5. I hope that's clear. And then when I calculate x, I get it as 2.25 meter. Because I'm interested in the vertical line drawn from the center of gravity falling within the base, so it's already out by 2.25. You could simply have taken it as half of 4.5 because this is exactly the center. Anyways, so you get this as 2.25. How much more could you go? You could go up to 1.25 more, because the maximum distance here is 3.5. Where did I get that from? The radius is 3.5, isn't it? So if this is already 2.25, the remaining is 3.5 minus 2.25, which is 1.25. So if this line can go 1.25 meter more, that means the line from the top can move double of that, which is 2.5 meter. I hope you got that. Here, this is about Young's modulus and 15 centimeter long tendon. That is the original length. It stretches 3.7 millimeters when a force of 13.4 Newton is applied. And the diameter of this is 8.5. You got to find the Young's modulus. This is just a direct substitution into the equation. Just made both into meters. Force is 13.4 newtons and area is pi r squared because the cross section is a circle. And what is given is the diameter, so I've got to take the radius in meters and square it. That's what I've done here. And then the formula for Young's modulus. Stress divided by strain. And all you have to do is substitute those numbers and calculate. When you do that, you get 9.58 times 10 to the 6 pascals. 9.58 times 10 to the 6 pascals. So some clearing up to be done here. Okay, that looks fine. See, the Young's modulus is always huge. Even for a tendon, it's that much. For steel, it's actually 2 times 10 to the 11 pascals, like I told you. In this question, you have a mass of 25 kilograms hung from the middle of a fixed straight aluminum wire. And because of that mass, the wire sags to make an angle of 12 degrees with the horizontal. Find the radius of the wire. Why does it sag? It sags because it stretches. And so we got to find how much it stretches from the angle given. Let me make that diagram. So that is how it looks. Of course, highly exaggerated. And there are tensions there. And this angle is 12 degrees, as you can see. Force is 25 times 9.8. Which is 245 newtons. And that's where we have to carefully understand what I've done. I've drawn a line at right angles to this one. So I've got a small, tiny right angle triangle there. Okay. And surely, looking at this figure, if I take half the length of this as L, then you know that this must be the same. Okay. Which means this is how much it did stretch. Are you getting it? That's how much one side stretched. Okay, that's what we're trying to find from this diagram. Okay, that's again a right angle triangle. And cos theta, I'm taking this as theta. We know it's 12. Cos is adjacent by hypotenuse. So when you do that, okay, let me show it to you. Cos theta is adjacent divided by this hypotenuse, which is L plus delta L there. And so you get this. Take the reciprocal, both sides. So now I can divide each one by this. So this becomes L by L, which is 1. And then I rearrange this side. You know why I'm doing all this? Because I need to find this ratio. Now I got it. It's 1 by cos 12 minus 1, which is 0.022. And once I get this ratio, that's the strain, I can put it back into the Young's modulus formula and make the area of cross-section the subject. Just take that there and bring the Young's modulus down and substitute the numbers given. And actually in this problem, the Young's modulus of aluminum will be given to you, which is 70 times 10 to the 9. I just forgot to write that number down, okay, in the problem. It will be given to you. And then you do this because it's the reciprocal of this, see? That's why I put 1 by 0.022. When you calculate, you get the, what is that? That's the area of cross-section. And from the area of cross-section, you can calculate the radius because A is pi r squared. I don't know whether I did that. Let's see. No, I did not. So going back to that problem, once you get the area of cross-section, please calculate A is equal to pi r squared and find the radius. The radius is the square root of A by pi. And I'm not going to calculate that, just calculate that, okay? In this next question, the center of gravity of a loaded truck depends on how the truck is packed, yes. Because if it's packed with heavier items at the bottom, then you know the center of gravity is going to come down. That's what we need to make it more stable. If it is 4 meters high and 2.4 meters wide and its center of gravity is 2.2 meter above the ground, how steep a slope can the truck be parked on without tipping over? Okay, let's get the diagram. That's the truck, that's how it looks. And that's the slope that you see. And that's how much the angle is with the horizontal. The base is given as, is it 2.4 meters? Okay, this is the idea, see. To find how much it can be tipped over to a maximum, you know, you have to draw a line, a vertical line from the center of gravity straight down, and if it falls just inside the base, like in this, like remember this is the base, so this line, vertical line from the center of gravity is just inside the base, so it will not tip over. That's a boundary condition. A little bit more to the side, it will go down. You won't get it back. So I've drawn the limiting condition here. So I've set up the triangles with that. So let's take this as X and that's H. These two angles are equal from the symmetry of the diagram. Therefore, look at that right angle triangle. Tan theta is X by H. Because if that's X, this is also X, okay? Opposite by adjacent. So tan theta is X by H. X is 1.2, half of 2.4. H is 2.2 given in the problem. So tan theta is 28.61 degrees. So which means you could place it on a slope of angle 28.61. If it's 28.62, say goodbye to the truck. Okay, these problems have been done already. Okay, so here it is, the problems on stable equilibrium and elasticity. Good luck.